Today we're going to start talking about kinds of mixtures that are especially important to chemists. The kinds of mixtures we call solutions, colloids, and suspensions. Most of this unit is going to be about solutions. We have to introduce you to the concept of colloids and suspensions as well. Okay? Now, I was told by a couple other classes that some of you actually made mayonnaise when you were in ninth grade. Has anybody did that? Okay. Mayonnaise, it turns out, is a colloid. Okay. But you can't use any of the tests we're going to talk about to test mayonnaise to find out if it's a colloid. It won't work. And that's a good example because we're getting into that part of the semester now, and we have been in the previous unit as well, where there is no black and white sort of way to figure something out, whether something's a solution or colloid or suspension. It's not one way to do it. And if this works, it's definitely this or definitely something else. Figuring out whether something is a solution or a colloid or a suspension takes some judgment based on different kinds of testing. Because certain types of colloids can be found to be colloids by certain kinds of testing. Other kinds of colloids can't be tested that way, for example. Okay? So the kinds of tests I'm going to talk about today for finding out if something is a colloid won't work at all for mayonnaise. All right? But it'll work for other kinds of colloids. So let's start by talking about suspensions, though. And you're familiar with suspensions. Most of you are anyway. Because most of you are familiar with chocolate milk. How many of you don't know? Anybody here doesn't know what chocolate milk is? Everybody knows what chocolate milk is, right? Okay. Now, if you buy the chocolate milk in the store that comes as chocolate milk, that's not really a suspension. But if you go home and put, and excuse me for talking about brand names, but Hershey's syrup and stir it up, or Nestle's Quick and stir it up, okay, that would be a suspension. What happens when you take that suspension, that chocolate milk made from Hershey's syrup, or Nestle's Quick, or one of the other brands, store brands or whatever, and you leave it in the refrigerator for an hour? The what goes to the bottom? The chocolate falls to the bottom. Okay? That's one test for a suspension. Okay? A suspension, you can know it's a suspension if, that's not the only test, but one test is if you leave it sitting undisturbed. It will separate on its own. Okay? If that happens, you've got a suspension. Like that lab we did where we made that lead to iodide. And the yellow stuff eventually settled on its own. Now, we didn't spend a lot of time waiting on it in here, but if we left it sitting for a long time, like a day, the next day, the liquid on the top would be almost completely clear. Okay? The longer you leave it sitting, the more the suspension settles. Got that? When you first put them together, first put the lead 2 nitrate solution together with the potassium iodide solution, you got a yellow mustard-looking color, didn't you? It was just all the way through there. But after you let it sit for a while and begin to separate, you can tell it was separating. Okay? That's a good example of a suspension. All right? Now, what I'm about to give you is not an absolute all the time, every day, always works idea. Okay? Remember in the previous unit, Unit 7, we talked about the factors that affect whether something is going to be a solid, liquid, or gas. I made a Venn diagram, this thing right here. This also applies to suspensions and colloids and solutions, okay? Because whether something is a suspension or a solution sometimes, or maybe a suspension or a colloid or a solution sometimes, depends on the strength of attraction between particles. Because I can have a large particle that would, in other cases, be a colloid, ends up being a solution because of the strength of attraction between particles. Okay? Or how fast the particles are moving, or the size and shape of particles. Okay? Let's go back to our suspension idea for just a minute. Suppose that I have chocolate milk, and I have a device that will stir that chocolate milk constantly, and I can put it all in the freezer. So I put my glass of chocolate milk in the freezer with something that stirs it. Eventually that chocolate milk freezes. And as long as it's frozen, the cocoa doesn't settle anymore, does it? Okay? Is it still a suspension? Yeah. Because if it were liquid and were undisturbed, it would settle out. That makes sense? Okay? So it's still a suspension even though it doesn't settle out. That's why I'm saying these tests don't always work all the time. Okay? It kind of depends on a lot of other things. Just like mayonnaise. Yeah, it doesn't settle out or it doesn't do any of the other things we do for determining when you have a colloid. All right. Something else you can do, and this also happened in that lab you mentioned there, for figuring out if you have a suspension, if you can filter it through normal filtration means, like we filtered the lead to iodide, and we got the stuff separated. Well, filtering, if you can filter it through a normal filter, gravity-fed filter, then it's a suspension. Okay, we can filter it out through normal means, through typical means, it's a suspension. Okay. Now, suspension particles are almost always going to be larger than 200 nanometers. In fact, most of them are going to be larger than 1,000 nanometers. But just for right now, let's just say they're larger than 200 nanometers. Okay? It really depends on these three factors. Attraction between particles, size and shape of particles, how fast the particles are moving. Okay? If I heat up the solution or heat up the mixture, something might not settle out on its own. But I cool it down, it might. Okay? So there's some judgment going on. And so whenever you're testing something to find out if it's a suspension or a colloid or a solution, it takes some good judgment. You got to kind of add all the pieces up and figure it out. Okay? Kind of like somebody's on trial, and all the evidence is circumstantial. You don't have direct black and white evidence. You got to add all the pieces up to figure out whether they're guilty or not. That makes sense? Okay? All right. Let's talk about colloids then for a minute. And we said that mayonnaise is a colloid, but mayonnaise can't be tested with any of the ways I'm going to talk about right now. Okay? Colloid particles typically, not always, are between 1 nanometer diameter and that 200 nanometer size. Now that's an average diameter, and there's a lot of factors that go into whether it actually fits that. But like I said, there are some colloidal particles that can be upwards of 1,000 nanometers and still be a colloidal particle. It has more to do with behavior than it does size. Okay? So the size of the particle isn't nearly as important as the behavior. That leads us to the conclusion of whether something is a colloid, suspension, or what I'll talk about in a minute, a solution. One way you can tell, and it doesn't always work as I said, one way you can tell that you've got colloidal particles is you try to filter it out, it doesn't work, but then you put the mixture in a dialysis tubing. And if the dialysis tubing separates out the part you mixed in from the part that is where it's being mixed, then that's a pretty good indication you've got a colloid. What'd you do it for? Okay. Okay. What do they use dialysis tubing for? Yeah, what do they use it for? All right. Okay, yeah. It's used to clean your blood. Okay, so dialysis tubing will take out the blood molecules, or not molecules, but cells, right? Which aren't really cells because they don't have a nucleus, isn't that right? Come on, you're not taking biology. Huh? Okay. Huh? Yeah. So dialysis tubing has a much smaller pore size. I don't mean pore like you pour a liquid. I mean pore like holes in something. Okay, porous. Huh? Like your skin's porous. Okay. All right, so dialysis tube, I said tube, I should say tubing, I guess, okay? Another test for whether something is a colloid only applies to a certain narrow category of colloids. Those colloids that you can see through, okay? Those colloids you can see through. They might have color in them, but if you can see through them, you can use this test to find out if it's a colloid or a solution. So if you can see through it, it's not always either one. But one way to tell if you have a colloid as opposed to a solution is when you shine a narrow beam of light, a really narrow beam of light through the colloid glows. If it doesn't glow, it's a solution. If it does glow, it's a colloid. And that's something that's called the Tyndall effect. I'm planning on it. It'll separate parts of a colloid some of the time, but it won't work for mayonnaise. Can you imagine trying to put mayonnaise in a dialysis tubing? Wouldn't work too good, would it? And it's not going to separate the parts of the colloid. Okay? NM is nanometers, yes. Unit 1. All right. And then we got solutions. Okay? Now solution particles, the part of the solution that's getting put into something else, if those particles are less than 1 nanometer, that's a good round number for figuring out that it's a solution particle. Okay? So we might say that a solution occurs when you have two substances mixed at the nanometer level. Does that make sense? The particles are a nanometer or smaller. That's pretty small. Yes? Okay? That doesn't mean that it always has to be, because it might be that the part that you're putting something into, that part has particles that are larger than that, but the part that's going into that is a nanometer or smaller. It could be, it's a lot of different things. Again, it goes back to those three different things where you have strength of attraction between particles, how fast the particles are moving, and size and shape of the particles. All that affects whether or not you're going to have a solution, a colloid, or a suspension to a degree. Okay? Well, the only way to separate out a solution, if you have a true solution, it takes a chemical separation process to separate the stuff out. Okay? To separate them requires a chemical separation process. Okay? A chemical separation process. There are lots and lots of these, and there are more tests about colloids and suspensions too. We're just not going to get into them right now. Okay? I'm only going to give you two examples for right now. And one of those examples is distillation. If you have to use distillation to separate out the parts of a mixture and nothing else really works, that mixture is a solution. Got that? So let's say I've got a mixture here and I'm trying to figure out, do I have a suspension, a colloid, or a solution? So the first thing I try to do is leave it sitting down on the table and leave it alone for a while and see what happens. And it doesn't settle out. Well, then I try to filter it. I can't filter it. I know it's not a suspension. At least I got a good chance to know that, okay? Doesn't always work, but that's a good way to tell. Does that make sense? Okay? Then I'm going to test it for a colloid. I'm going to take and put that mixture into a dialysis tubing and find a way to figure out if the particles are separating out. So maybe inside the dialysis tubing, and I won't show the tubing as being this, it's not really a cylinder, but inside I've got the mixture I'm testing, and outside I've got some chemical that reacts with the part that's being mixed up in there. Okay? So if the stuff comes out, I get a color change, or I get a temperature change, or I get some kind of chemical process that tells me that stuff inside is migrated out. Well, I'm pretty sure I got a colloid. Does that make sense? Okay? All right. Now, if that won't work, and here's another way to tell if you got a colloid. sometimes. You can't separate it out by filtration, but you put it in a test tube and put it in a centrifuge. All right, let's call it centrifugation. Okay? You spin it. So essentially what you're doing is increasing the amount of gravity. So it won't settle out under normal gravity, but it settles out under increasing gravity because we do this centrifugation process. So I spin it really, really fast. If that'll separate it, I've got a colloid. Okay? So Mona Leah, you're big into anatomy. What material are you familiar with that won't separate by settling, but will separate by centrifugation? Yes? DNA? Blood is the one I was thinking of, DNA. Actually, there's a process, part of the DNA separation process, where you can do that. That's true. Okay? But you don't normally separate out until you break everything else up. Yes, you would get it. You would eventually get that. So getting these DNA strands, or it's like stuff that comes out of your nose. After a while, there's several steps in there where you do this centrifugation process to separate out the DNA from the stuff you got it mixed in. That's true. Okay, so if you've ever done that, you know what I'm talking about. So it was a suspension. It was a colloid to start with, and you separated it by. But sometimes you got to be careful, because sometimes with that DNA, if you leave it sitting undisturbed, it would settle out on its own. You only centrifuged it to speed it up. Okay, so if you ever have that opportunity, you can try and set a piece aside and see if it'll settle on its own. And it depends on the size of the DNA chunks you got. Okay, so I've done that before, and I know it will separate on its own eventually, but you don't usually have that much time. All right. But blood, on the other hand, will not separate it out on its own. But so you use centrifugation to get that. So blood is a colloid. Okay? All right. So distillation. You know what happens with distillation? No. Well, usually you boil it, then you collect the gas part of it and recondense it. And so the stuff that didn't boil out stays behind. The stuff that did boil out, you collect at the end. That's how you'd have distilled water. But it's also how you distill alcohol. And what it does is take advantage of the different boiling points between alcohol and water. So water boils at a lower temperature than the alcohol does because water is more polar. Very good, okay? So water is going to boil at a lower temperature. Alcohol is going to boil at a higher temperature. So as long as you keep the temperature of that solution that's boiling just at the point where it begins to boil and don't heat it up a whole lot more, mostly what leaves in the vapors anyway is the alcohol. No, the OH in the alcohol is what allows you to dissolve the alcohol in the water to start with. And so you separate it out by taking advantage of the differences in the boiling temperature. Now, the solution, the stuff you get at the end, when you condense that alcohol back to a liquid, still has some water in it. It's not a perfect separation process. In fact, if I were separating out ethanol, so I take sugar water, put some yeast in there, make some alcohol, and I distill it. The product I get out of that distillation is probably about 96, if I'm really good at it, it's about 96% alcohol. After that, I just about can't get any better than that. They have come up with some distillation processes that get up to about 98%, which we don't have the technology to do that here at Dorman High School, but you could do that, okay, supposedly. I would love to have some of those distillation columns to do that. But anyway, and you can take that distillation product, the alcohol, and distill it again, huh? To make alcohol? Yeah. I mean, yeast and sugar? You're not going to drink the stuff. Yeah. No, we're not going to make corn mash here or anything, No, that would not be allowed. Okay? I mean, look, there aren't, huh? There are, you can add ethanol to your gasoline, right? When they do that, you buy it like that, right? No, it's 85% alcohol, 15% is alcohol. 85%. They call it 85% ethanol, which doesn't really mean 8. Yeah, they call it E85. That's right. Depends on the car. Anyway, the point is that that's kind of a misnomer. I wish they would say but you know what? What are you going to call it? 85% gasoline? Nobody would know what that means. So they call it E85 ethanol because at least it tells people there's ethanol in there. Okay. Well, you can actually it's legal to make a certain amount of alcohol at home, and you can run your cars on it if you want to. Okay. I wouldn't. I don't know. I mean, we could do that. Actually, if there are schools where, as a project, the science department and some of the students make diesel fuel out of used kitchen oil. You know, and part of that process means you've got to add alcohol to that. So they do some distillation that way for that purpose. Okay. And it's a neat project. It's just kind of really time consuming and takes a long time to get it done. But anyway, all right. Another of the chemical processes we're going to talk about today. There are a lot of them. I'll talk about some more later on. But just for a couple of examples today, another one you may be familiar with is called crystallization. Okay, crystallization. Anybody ever made rock candy?
Yeah.
That's crystallization. So with rock candy, basically what you're doing is you're dissolving sugar in water, and tell me if I'm wrong now, because I never made it myself. Yeah. Take sugar and water, and then you boil it. And you boil away a lot of the water, and eventually you get to this point where there's a lot of sugar in there and not a whole lot of water anymore. And then you start it crystallizing, and it starts building up on the stick, right? Is that pretty much it? Yeah, the crystals would help seed it, start it going. You're right. I can see that. All right. So what you do, we'll talk about this later, but it's called a supersaturated solution. Okay. And actually, water and sugar form something called an azeotrope. It's really cool. But anyway, we'll go to that later. All right. So let's say, for example, here's another crystallization process. Stir some salt and some water. Okay. On an open glass. Leave it on the kitchen counter. What happens? The water evaporates out. What's left behind? The salt. That's crystallization. Just a different way of doing it. Okay? There are certain types of chemicals where you dissolve it in water and you just put it in a refrigerator and it crystallizes out. Okay? That's another way of doing it. So there are a lot of ways to do crystallization, but that's another way to get things out in a chemical process. It takes advantage of the chemical properties of the substances and not the physical properties. All these separation processes up here with suspensions and colloids all take advantage of physical separation processes. Okay? Centrifugation increases gravity. That's a physical separation process. The Tyndall effect has to do with the way that light reflects in those particles. Dialysis tubing, we're separating by size. Filtration, separating by size. Separating by settling, that's just taking advantage of the size. Okay? That makes them separate out. There's still all that stuff about attraction between particles, how fast they're moving, shape of the particles. All that comes into play, but basically these are all chemical or physical separation processes, and these are all chemical separation processes that take advantage of the chemical properties of the particles that are mixed together. Okay? And that's the key difference between these two and solutions. Suspensions and colloids are held together by, or can be separated by physical processes. Solutions can be separated by chemical processes. Okay? And that's the key way to tell whether you've got this or one of these. Okay? Not always absolutely true, but almost always. Really much better than any of these others. All right? Now, let's talk about what makes up a solution here. All right? We need to talk about how we define a solution a little bit. Okay? A solution always, in terms of our definition and understanding of solution, a solution always has two parts. Something that is dissolved and something that does the dissolving. If I'm dissolving salt in water, the salt gets dissolved, the water does the dissolving. Okay? Oh, this sounds like a lot of the stuff we talked about in this past unit, doesn't it? Okay? When does water dissolve things or not? Yes? Okay? All right. So the part that gets dissolved is called the solute. That's the name we give to any part in a solution that gets dissolved. So this is the part of the solution that gets dissolved. Okay? Now we also have the other part of it, and that's the solvent. Now you could have more than one solute, but you can usually only have one solvent. How about something that we really like in the South, it's a staple of the South, iced tea. What? What? Sweet tea. There you go. Sweet iced tea, right? Yeah. I mean, some people drink it without sugar, but come on. In the South, it's sweet tea. It's got to be. Okay? All right. In sweet tea, there's only one solvent. What's the solvent? Water. All right. There's more than one solute. The tea or the sugar you're not thinking. But actually the tea has more than one part. You've got some tannic acid, some other things that give it its particular flavor. Okay, it depends on the kind of tea too. Okay. It's a weak organic acid, and all plants have tannic acid in them. Okay.
So is it natural?
Yeah, it's natural. Sure. In fact, it's used in tanning hides. That's where we got the name from it in the beginning. If you take, for instance, if you gather up a lot of acorns from an oak tree, and you crush them down and do some boiling and things like that, you get a pretty concentrated solution of tannic acid, and you use that to treat animal hides for tanning. Okay, that's one way to do it. There's a lot of other ways to do it too. But if you go, you know where the Okefenokee Swamp is? All right, in southeast Georgia is a region of the state that was one time under the ocean, and there was a giant, really huge reef right near the coast of what is now Georgia. And so when the water level dropped, you had this sort of ridge along the edge of Georgia, okay, and the water all kind of gets stuck in behind that. And it's a really, really shallow lake, which really isn't a lake because it's so shallow. It's a swamp. It's huge. It's called the Okefenokee Swamp. The water in the Okefenokee Swamp, it's a swamp, but you can drink the stuff. Perfectly safe. The reason why is the tannic acid. All that dead grass and trees and stuff that falls down in there and settles at the bottom, they release tannic acid. It kills all the bacteria. Perfectly safe to drink the water in the swamp, at least in the Okefenokee Swamp. Not every swamp necessarily, okay? So don't just go out and start drinking swamp water now, okay? Got that? All right. You can't really, it tastes a little bit acidic, but you can't, doesn't really taste much. Huh? Yeah. I've been in the Okefenokee Swamp, sure. I always wanted to take my sons I just never had a chance to do it. You rent these canoes, and you take them, it takes about a week to canoe across the Okefenokee Swamp. It's really cool. Huh? Okefenokee. And the cool thing is, you think about swamps, you think about snakes, you think about mosquitoes, and there are snakes there, but there aren't any mosquitoes. Mosquitoes need shallow water, and the swamp, Okefenokee Swamp water is too deep. There are almost no mosquitoes. Really cool, you know? There are some islands there, and there'll be some mosquitoes in the islands, but most of the swamp has no. Oh, and that's where the floating. You know what floating islands are? That's what's really cool. It's like all this dead grass and leaves and stuff. They all float on the top, and more grass grows up in that floating stuff, and more and plants grow up in it. And it's like an island, but you walk out on it, it's mushy. Okay, and you can walk on it, but you got to be careful because occasionally you fall through too. But they're called floating islands. But the whole point, it's just neat.
How deep is it?
I think on average like 8 feet deep or something, 12 feet. It's not very deep, you know. But it's really cool. The whole thing's really cool. And there are a lot of alligators there. And alligators, by the way, alligators don't attack people unless you get around their babies or the eggs. You guys gotta know what to watch for, you know. So at night when you go frog gigging in the swamps, okay, you look for the eyes that reflect in the lights you're shining out there. If the two little points of light turn red, that's a mama gator. Go away. Okay, Long story. We'll go there. All right, solvent. That's the part that does the dissolving then, okay? We got way off track there, didn't we?
No, we didn't.
Not at all.
Yeah, that's true, but I mean all that stuff about alligators and floating islands.
It all had to do with
That's true. It does have to do with tannic acid. Part of the solution that does the dissolving. All right. So we're talking about distilling alcohols a while ago, and I sort of went down that road for a reason, because it turns out alcohols are one of those solutions, because alcohols are almost always a little bit of water and a lot of alcohol, okay? But it's one of those solutions that this definition doesn't work for. So when you go to the store, Walmart, the grocery store, the drugstore, and you buy rubbing alcohol, it says one of two percentages on there. 91 or 71 usually. I think it's 71, okay? So that means that it's 71% alcohol, 29% water, or 91% alcohol, 9% water. Okay? It's almost impossible to get all the water out of an alcohol. But here's the problem. In that case, alcohol can be in any percentage. I can have 2% alcohol, I can have 98% theoretically alcohol. Okay? Which one of the two, the water or the alcohol, is the solvent? Because you're not really dissolving one in the other. They're both dissolved in each other. Does that make sense?
Is that things like proofs and whiskey?
That's exactly what proofs in whiskey are about, yes. Okay? The question then is, how do we define what the solute and solvent is when it's not so clear like that? When it's not so clear, when you can't so easily tell what's getting dissolved and what is doing the dissolving. In that case, you have a fallback definition. And the fallback definition, when this doesn't work, is the part of the solution in greatest concentration is the solvent. The part of the solution in greatest concentration is the solvent. And everything else is the solute. The part of the solution in greatest concentration is the solvent. So if I have 71% alcohol, that's 71% alcohol, 29% water, what's the solvent? Alcohol. That's not what we usually think about, but that's the way it works.
That's the solvent.
That's, yeah, because it's in the greatest concentration. Okay? That make sense? All right? And there are a lot of these that, this sounds like black and white. Not so black and white. Sometimes not so easy to tell what's going on. Okay? We won't get into that too much. We'll try to keep it pretty simple, at least when you first start learning about solutions and solvents and all that kind of stuff. Okay? Any questions about it so far? Are we good? All right. So how do we figure out how strong the concentration is? We're talking about alcohols, and since we just talked about those, I'm going to go with that first, okay? That's percentages. And whenever your concentration, that's what we're going to talk about now, very briefly in the time we have left, I'm going to introduce you to the concept of concentration. If we're talking about percent, which we can write as like this, okay? And it doesn't tell you anything else but percent. Then it's assumed that it's percent by mass. If nothing else is listed there by percent, then you're going to assume percent by mass. Okay? So, mass divided by mass times 100. That makes sense? That's a percent if it doesn't say anything else but percent. Now here's the tricky part. You got to be careful about this. Let's say, for example, and I'm just going to write this on a separate sheet of paper here because I don't want to mix up the notes here. Let's say you find a label that says percent V over V. That's not percent by mass anymore. Percent by volume. Very good. Percent by volume. Okay? And there are rare cases, and it shouldn't be done this way. You've heard me say this before. Nobody should do a percent where you mix up the units of measurement. I've seen percent where you have mass over volume. Oh my gracious, don't do that. Okay? But they do it sometimes. Okay?
Would that be like percent?
I don't know what that is. Don't ask me. I teach chemistry. They do it in the food service industry sometimes. That's fine, because that's not mixing up units. Okay? This is mixing up units of measurement. We don't want to do that. All right?
It's not like percent density.
That'd be kind of like percent density, wouldn't it? But it's not density. Okay? It's not a true percent when you're mixing the units of measurement. Okay? Anyway, so that's one way of doing it, and that's pretty simple. We find the mass of one part. Usually it's the solute that you find the mass of, and you divide it by the mass of the solution. So you take the mass of the solute and divide it by the mass of the solution. Because the solution is everything. The solution is made of, and this is from the notes we had just a minute ago, the solution is both the solute and the solvent together. So the mass of the solution is the mass of the solute plus the mass of the solvent, right? So this is mass of solute, mass of solution times 100. And that'll give us a percent. And that's how alcohols in the store are usually listed. Okay? 71%. It's the mass of the alcohol is 71 for every 100 grams, let's say, of the solution itself. Well, that's not the way we do. You could, but that's not the way you do. Let's keep it simple. Let's keep it simple, okay? This is the way we want to think about percents, all right?
So in alcohol,
And with alcohols, that's what they actually do. They have the mass, because I defined the alcohol as the solvent is the alcohol, right? So they say 71% ethanol. I mean, isopropyl alcohol. That's actually saying that's 71%, 71 of the solvent over the solution. So that's really not great, but it's okay. All right? That makes sense? So really, whenever you have a percent, it should be less than 50 if you're doing it correctly. At least in the way I teach it here, okay? Yes? Because generally speaking, the mass of the solute should be half, at least half or less.
because it needs to be less.
Yes, it's the one in smallest concentration. That's not always true. Let's say you're dissolving some solute that actually has a greater density, okay, than the density of the solution itself. You could have more than 50%, but it can't be a whole lot more, I wouldn't think. All right? All right, now, that's one type of concentration unit. Another concentration unit is called molarity. Well, if it says molarity, what do you think one of the measurement units is going to be? Moles. There you go. And not the kind that digs tunnels in a yard. Okay? All right, moles. Molarity, and by the way, the symbol for molarity is also a capital M. Oh no, we just used a capital M for something else, didn't we? Okay? This is a unit of measurement, and usually is not used to mean the variable, although it sometimes means both. But when you're writing it out, here's how we tell the difference. Put a line under it. Okay? Molarity is a capital M. I haven't defined it for you yet, but we know that moles is one of the two units of measurement. Okay? With molarity, you're going to take the moles of the solute, S-O-L, moles of the solute, over liters of the solution. Moles of solute over liters of solution. Moles per liter. Okay? So you could also say molarity, at least in terms of units, will always give you moles per liter. Does that make sense to you? Got that? All right. Last unit of measurement we're going to talk about today, and this is the one that Frank really wants to know about. What lab is Frank always talking about? Molality. What is the lab you're always talking about wanting to do? Huh? Ice cream. This is the one we need for ice cream. Okay? Now look, molality, molarity. Gotta be careful. Two different ways of measuring concentration. But this also has moles in it. This one happens to be moles of solute over kilograms of not solution, but solvent. Okay. Because it's typically, you just have to know the context here. It's contextual. Okay. So molality then is going to come out and be units of moles over kilograms. Got that?
I guess they didn't know that mass isn't involved in
That's, yeah. So, why do we have this, and why is it important in the ice cream lab? And here's why. Without getting too deep into it, when we're calculating energy exchange, this makes the most sense mathematically. When we do all the testing with it, you find out that this unit of concentration gives us a better result for figuring out the way the energy is being transferred from one place to another. And that's what making ice cream is taking the heat energy out of the ice cream mix so that it'll freeze. Okay? And that's another set of calculations, but you'll have to use this when we get to that unit because you can't make ice cream unless you can do the calculations. Okay?
Oh, you don't make ice cream in here?
That depends. That depends. It depends on whether we get through the material. It's the last unit. You know, we got to get through everything. That's why we got to do that little bit of extra homework and a little bit of extra video lessons and stuff like that so we can get to that ice cream lab. That's a whole day. Whole day out making ice cream, and you got to be able to do the calculations first. Huh? Yeah, that little ball thing, yes. You have one of those? Okay. Oh, yeah? Okay. That's how we're going to make ice cream. We'll go outside. We'll do our thing. You know, basically you play with the things until it makes ice cream. Pretty cool. But you got to do all the work first. You got to do all the calculations first. All right? Any questions about that? All right. But now look, let me tell you one last thing. Molarity is the one we most often use in the lab. Molarity is the one we most often use in the lab. That's the one you need to be most familiar with.